Hello, this is Dr. Joe Trout from the physics program at the Richard Stockton College of New Jersey. In this lecture, we'll discuss Chapter 9. Chapter 9 deals with the atmosphere's planetary circulation. So the driving question for this chapter is, what are the principal features of the planetary scale circulation? And how does the circulation affect weather and climate? In this chapter, we'll discuss planetary scale pressure systems, wind belts, circulation patterns of the middle latitude westerlies, and anomalies to our regular patterns. So for example, El Niño and La Niña. Let's start with an idealized planet, one that's not spinning. We said we'd find the most intense sunlight at the equator, and what will happen is the sunlight would travel through the atmosphere, strike the Earth, and it'll be most intense at the equator. So the air above the equator would become hot. It would rise up through the atmosphere, and cold air from the poles would come down to fill in. The air that was rising would hit the top of the tropopause and would flow around in this pattern. So we'd have ascent at the equator and descent or subsidence at the poles. So convection cells would form when the cold, dense air sinks at the poles and flows at the surface towards the equator, where it forces warm, less dense air to rise. Aloft the equator, air flows towards the poles. So at the equator, we get convergence at the surface and divergence aloft. But don't forget, we also have the Coriolis effect. So if this idealized planet starts to rotate, the Coriolis effect will come into play. What we'll see is that the air that's flowing down from the North Pole would begin to curve, and the air flowing up from the South Pole would begin to curve. So the northern hemisphere, the surface winds are diverted to the right and blow towards the southwest. And in the southern hemisphere, the surface winds are diverted to the left and blow to the northwest. So the winds blow counter to the planet's direction of rotation. Circulation is going to be maintained in the atmosphere of our idealized planet Earth because the planetary scale winds are going to split into three belts. These three belts occur at 0 to 30 and 30 to 60 and 60 to 90. Some winds blow with the rotation of the Earth, and some winds blow against the rotation of the Earth. So we see that surface winds are going to converge along the equator and along 60 degrees latitude circles. This convergence at the surface is going to lead to rising air and expansional cooling and cloud development and precipitation. The convergence zones are belts of relatively low surface air pressure. So if we go back one slide, we see at 0 degrees along the equator, we get convergence. And we also see that at 60 degrees, we also get convergence. At 30 degrees, we see that we get divergence. So at 30 degrees north and 30 degrees south, we get divergence. So surface winds are diverge at the poles and along 30 degrees north and 30 degrees south latitude circles. Here air is going to descend. It's compressed and warms, and the weather is generally fair. Divergence zones are belts of relatively high surface air pressure. So now let's add in continents and ocean basins into our idealized planet, and we see this starts to complicate the picture. So what you see is along 0 degrees, so along the equator, we see some lows. And at about 30 degrees, we see some highs. And 30 degrees north, we see some highs. Along 60 degrees, we see these lows. And at negative 60 degrees, we'll also see these lows. So some of these pressure belts break into separate cells, and the important pressure contrast develops over the land and versus the sea. And the map shows the mean surface level pressure, and the top one is January and the bottom one is July. So we call these semi-permanent features. So for instance, we have a high at 30 degrees north latitude. And that high shifts up and down a little bit between the summer and winter, but it's pretty much in that general area. So we call these semi-permanent features. So now to simplify things, what we see is that we have these highs at 30 degrees north and 30 degrees south. And in the northern hemisphere, air is going to circulate around them in a clockwise direction. And in the southern hemisphere, it's going to circulate around in a counterclockwise direction. What this is going to do is cause winds to converge at the equator, and we call this the ITCZ, or the Intertropical Convergence Zone, and it also is called the equatorial trough because we have lows there. The winds that blow in to form this convergence are called the trade winds. We also have the subtropical anticyclones, these high pressure systems, that once again are semi-permanent. We also have the polar westerlies and what's known as the polar front up at about 60 degrees north and 60 degrees south. Except in the south, instead of having the polar westerlies, we have the polar easterlies. If we look at these subtropical anticyclones, they formed near 30 degrees north and south latitudes over the oceans. and they extend from the ocean surface to the tropopause and exert a major influence on the weather and climate over vast areas of the ocean and the continents. When we have subsiding air, which extends outward from the eastern sides, we get compressional warming and low relative humidity and fair skies. Major deserts are actually located on the eastern flanks. The far western portions are characterized by less subsidence, less stable air, and frequent episodes of cloudy, stormy weather. Along with the subtropical anticyclones, there is a weak horizontal pressure gradient over a large area. So the winds are weak, and we call these the horse latitudes, and they run 30 to 35 degrees north and south. Since the winds are weak, the reason they call these the horse latitudes is that sailing ships would often get stuck in these weak winds and be unable to move very fast because the winds aren't blowing the sails very fast. So they would have to dump anything that's heavy and isn't necessary for life. So they would have horses on board to do some of the heavy pulling and work, and they'd have to throw the horses over when they got stuck in these horse latitudes. So surface winds, poleward of the horse latitudes, are called the mid-latitude westerlies. And wind blowing out of the high pressure cells towards the equatorial lows are called the trade winds. And the trade winds from the two hemispheres converge into a broad east-west equatorial belt of light and variable winds called the doldrums. In this belt, ascending air induces cloudiness and rainfall, and the most active weather develops along the intertropical convergence zone, the ITCZ, as we showed on the map. If we look poleward of the subtropical anticyclones, we see that surface westerlies flow into this region of low pressure. And these are the Aleutian low and the Icelandic low in the northern hemisphere. In the southern hemisphere, this is a nearly continuous belt of low pressure surrounding Antarctica. These surface westerlies meet and override the polar easterlies along this front. In the places where this polar front is well defined, it is a potential site for the development of extratropical cyclones. So polar highs are shallow, cold anticyclones that develop at high latitudes. So as we look at this diagram here, we note that it's a kind of a strange view. Here is the equator in the intertropical conversion zone. Here is north 30 degrees and south 30 degrees. Once again, what we have is the sun comes in and heats the equator. This brings warm air, warm moist air, aloft, and clouds form. At the top of the troposphere, at the tropopause, we get divergence, and some of the winds head north and some of the winds head south. Meanwhile, we get the trade winds that are going to fill in where this warm, moist air was sent aloft. So this circulation pattern, this cell of winds, is called the Hadley cell. So if we look aloft, the winds in the middle and upper troposphere blow away from the intertropical conversion zone. And these feed into the subtropical highs, and the resultant convection cells are known as Hadley cells. If we look aloft in the middle latitudes, what we're going to see is that the winds blow from west to east in a wave-like patterns of ridges and troughs. So once again we see that in the northern hemisphere the winds blow counterclockwise around lows and blow clockwise around highs. So what happens is we get, if we have a low here and a high here and a low here, we'll get this wave pattern that will start to develop. So here's the top of the wave, the ridge, and here's the lower parts of the wave, the trough. These winds are responsible for movement of synoptic scale weather systems, and their north-south components contribute to the poleward heat transport. So if we look at a cross-section of the Earth, what happens is we have the Hadley convection shells shown here. Once again, the sun hits very hot here. It's very intense, causes that air to rise. Cold air comes in and fills in. It hits the hot type of the troposphere, called the tropopause, and we get patterns that look like this. At 30 degrees north, we get divergence. And what we have here is a permanent front called the polar front. So this is cold air to the north of the front and warm air to the south of the front. We see that the tropopause is higher near the equator than it is near the poles, and it isn't a smooth transition. So for instance, here shows the middle latitude tropopause. Once again, at 60 degrees, we get convergence, and this is the jet stream. And what we'll see is a trade wind inversion. So there's a persistent and climatically significant feature of the planetary scale circulation over the eastern portion of the tropical ocean basins. Key to this formation is the descending branch of the Hadley cells. So descending air is warmed by compression, and its relatively humidity decreases. This air encounters the marine air layer overlying the ocean surfaces. Where the sea surface temperatures are low, the layer is cool, humid, and stable. Where the sea surface temperatures are high, the layer is warm, more humid, less stable, and well mixed by convection. The trade wind inversion is formed at the altitude where the subsiding air from above meets the top of the marine layer, trapping this cool marine layer near the surface. So it develops east and southeast of the center of the tropical high, and it acts as a cap on the vertical development of clouds and rain. We also see that seasonal shifts take place. So the pressure systems, the polar front, the planetary wind belts, and the ITCZ, the intertropical conversion zone, follow the sun. So what's going to happen is they're going to shift poleward in the spring and shift towards the equator in autumn. So the planetary scale systems in both hemispheres move both north and south in tandem. This means that the subtropical anticyclones are going to exert higher surface pressure in the summer. And the Icelandic lows deepens in the winter and weakens in the summer. And the Aleutian low disappears completely in the summer. Seasonal reversers of this pressure occur over the continents due to a contrast in solar heating of sea versus land. Continents at middle and high latitudes are dominated by relative high pressure in the winter and low pressure in the summer. As the ITCZ moves northward, it's going to trigger the summer monsoon rains in Central America, North America, India, and Southeast Asia. So here shows the position of the intertropical conversion zone in July and January. So in July, it's going to reach far north. And in January, it's going to be the furthest south. So here shows two cities at the same latitude, but they have very different climates. So if you look at the precipitation in San Diego, California, what we see is that during the winter months, we have high precipitation. And during May, June, July, August, and September, we have very little precipitation. In the winter months, our precipitation is 4 to 6 centimeters. Charleston, on the other hand, during the summer months of May, June, July, and August, and September, have very large amounts of precipitation, about 18 centimeters max. And they have less precipitation in the winter, about 8 to 10 centimeters. What we see is San Diego is under the eastern edge of the Hawaiian subtropical high and has a distinct dry season. Charleston is on the humid, unstable side of the Bermuda High, which causes it to have a very rainy summer. We also see that ocean surface currents play an important factor. So the surface ocean currents are wind-driven. Their horizontal movement of the ocean surface waters to a large extent mirror the long-term average planetary scale atmospheric circulation. Gyres, which are large-scale circulation regimes, appear in each of the major ocean basins and are associated with the prevailing winds that help set up the currents. So the trade winds in the westerlies, associated with the semi-permanent tropical highs, drive the subtropic gyres, which are these large circulation regimes. The counterclockwise surface winds in the Aleutians and the Icelandic subpolar low pressure systems drive the subpolar circulation. So if this is a map of our planetary scale circulation and the ocean currents that are wind driven. And we find out that the long-term average pattern of the wind-driven ocean's surface currents. And we get these circulation patterns that develop in the oceans. Now normally in New Jersey, what we expect is we have warm summers and cold winters, and followed by a warm summer and a cold winter. And it oscillates back and forth between this cold winter and the hot summers. This isn't true for places like India. What we see is that we get these seasonal reversals of prevailing winds. And this results in wet summers and relatively dry winters. So we see as vigorous monsoons over portions of Africa and Asia where the rains are essential for drinking water and agriculture. So over much of India, the monsoon rains account for over 80% of the annual precipitation. And it depends on the seasonal shifting of these global circulation patterns. They also depend on seasonal contrast in heating and cooling of land and water. So don't forget the oceans have a much greater thermal inertia than the land. So it takes longer for the oceans to warm up, and once they're warm, it takes longer for them to cool off. So we see as these surface wind patterns over Asia and what we'll see is a wet summer monsoon, and that's in picture A, and we see a dry winter monsoon in B. What's happening in A is we're getting wind that blows off of the ocean onto the land. So in the winter we get this wet monsoon, and these winds carry in warm, moist water, warm, moist winds off of the Arabian Sea. In the winter, the circulation pattern changes, and the wind blows off of the land onto the sea. So in the spring, there's relatively cool air over the ocean and relatively warm air over the land. So this produces a horizontal pressure gradient that's directed from the land to the sea. Directed from the sea to the land. This produces an onshore flow of humid air. Over the land, intense solar heating generates convection, and expansional cooling causes condensation, clouds, and rain. This release of latent heat increases the buoyancy, and it actually contributes to the uplift and instability, triggering even more cloud development and rainfall. Aloft, the air spreads seaward and subsides over the relatively cool ocean surface. So in autumn, the radiational cooling chills the land more than the adjacent ocean. So the horizontal pressure gradient is directed from the land to the sea. This produces an offshore flow of air. And over the land, air subsides and dry surface winds sweep seaward. Air rises over the relatively warm ocean surface, completing the monsoon circulation. So, unlike New Jersey, where we would see a cold January, and then a hot August, and then a cold December, what we see is that we have a hot, dry winter and a hot, wet summer. So the topography complicates the monsoon circulation and the geographical distribution of rainfall. The monsoon rainfall is neither uniform nor continual. So the rainy season consists of active and dormant phases. The planetary circulation, for example, the intertropical conversion zone shifting, and the strength of the distribution of convective activity vary one year to the next. So these variations are going to affect the intensity and duration of the monsoon rains. The southwest monsoon affects the American Southwest and brings dramatic increases in rainfall during July and August. We also see that we have these waves in the westerly, and there's between 2 and 5 generally encircle the planet at any one time. And these waves are called Rossby waves, and they're characterized, the westerlies, above the 500 millibar level. They're measured by wavelength, that's distance between successive troughs or ridges, and amplitude, their north and south extent, and the number of waves. In winter, the waves strengthen, so there's fewer waves, a longer wavelength, and a greater amplitude. And these seasonal changes stem from variations in the north-south air pressure gradient, which is steeper in the winter because of the greater temperature gradient. So we get zonal and meridional flow patterns, and the westerlies have two components, a north-south airflow and a west-to-east airflow. If the north-south component is weak, the result is a zonal flow pattern. So what happens is the north-south exchange of air masses is minimal. If the flow in this pattern of deep trough and sharp ridges, the result is a meridional flow pattern, and greater temperature contrasts develop across the United States and southern Canada. And the stage would be set for the development of an extratropical cyclone. If the northern westerlies have a wave configuration differing from the southern westerlies, a complicated split flow pattern can exist. So here we see the westerlies and the waves that are being formed. And here we see two images which illustrates the extremes of zonal and meridional flow. So once again, if we wanted to measure the wavelength of this, we go from say trough to trough and measure the distance. We'd also measure the number of waves that go around the Earth. And the amplitude is how far north they go and how far south they go. So these westerlies generally shift back and forth between these two configurations, between the zonal and meridional flow. And there is no regularity to this shift. And this affects the long-range weather forecasting accuracy. So what we see are highs being formed here and lows being formed here, and we get these waves that occur. Occasionally a blocking system and we'll get weather extremes. So in the North American weather is more dramatic when the westerlies are strongly meridional. So what we get are these undulations may become so dramatic that the masses of air separate from the flow. And what happens is we get this pinching off or the cutoff highs and lows result. And these prevent the normal west to east circulation, and they're called blocking systems. As you can imagine, this is going to bring extremes in weather such as droughts or flooding rains, or excess of heat or cold can result from these. So the blocking systems and weather extremes, we see that in A, what we have are these prevailing circulation patterns in the mid to upper troposphere during the summer of 1988. And these blocking warm anticyclones over the central United States contributed to severe droughts. So once again, here we have the westerlies, and we cut off with these blocking pressure systems, and what we end up with are droughts in Middle America in the summer of 1988. B shows the long-term average circulation pattern, what it should look like. So this map illustrates the principal features of the prevailing atmospheric circulation patterns during the summer of 1993. So here a blocking circulation pattern was responsible for record flooding in the Midwest and drought over the Southeast. So here we had a high pressure system and the air moving clockwise around that high pressure system. And we're bringing off hot, moist winds onto the center of the United States. Leaving a drought down in the southeast. So here the top map illustrates the total rainfall for June and August in 1993 expressed as percentages of the long-term average. So this very dark green is over 150%, and this lightest green is less than 50%. So heavy rains falling on the drainage basin of the Missouri and upper Mississippi rivers saturated soil and triggered excessive runoff and all-time record river crests and severe flooding, and the property damage totaled about $26 billion. We can also see short waves. These are ripples superimposed on the long Rossby waves. And they propagate rapidly through the Rossby waves. And we can get 12 or more waves are generally found in any hemisphere at one time. And these westerlies accelerate in ridges and slow in troughs. So what we're going to see is that the wind's going to slow and converge as we enter into the trough, and it's going to speed up and diverge as it goes into a ridge. So what's going to happen here is we're going to see at the highs subsidence and at the lows ascent, and we're going to see convergence at the lows and divergence at the highs. Probably everyone has heard the term jet stream, and what these are narrow corridors of very strong winds. They're in the middle latitudes, and the most prominent jet streams, the polar front jet stream, is located above the polar front in the upper troposphere between the mid-latitude tropopause and the polar tropopause. They follow the paths of the planetary westerly waves, and the winds can top up to 100 miles per hour or 160 kilometers per hour. So our eastbound aircraft seek these as a tailwind to speed up their journey. So the polar front is a narrow transition zone between the relatively cold and warm air masses. So cold air is denser than warm air, so the pressure drops more rapidly in a column of cold air than it does in warm air. So even if the air pressure is the same at the surface, there'll be a huge horizontal pressure gradient aloft directed from the cold warm air to the cold air. And that increases with increasing altitude. So what we're saying here is that here we have low pressure. Here we have um, a low pressure and a high pressure. And at the surface, if I look at this isobar, it's pretty much at the same height. But we said that cold air is denser than warm air, so the pressure drops more rapidly. So for instance, here we go from 200 millibars to 300 millibars to 400 millibars, right? At the same time, we went from 500 millibars to 600 millibars. So if we look at the horizontal pressure gradient, at the surface it's about zero. But if we get up to the 200 millibar height and we go straight across, there's a pressure gradient of 500 millibars to 200 millibars. So this is going to be directed from the warm air to the cold air. And this pressure gradient gets worse as you go up in altitude. So we see is that this Coriolis effect is going to balance the horizontal pressure gradient force. And the winds are going to blow parallel to the polar front with the cold air on the left of the direction of motion in the northern hemisphere. Due to a strengthening horizontal pressure gradient with increasing altitude, the wind speed increases with altitude in the troposphere, and it's highest near the tropopause. Where the polar front is well defined, the jet stream winds are stronger and jet streaks may develop. The strongest jet streaks develop in the winter along the east coast of North America and Asia. So we have this great temperature contrast between the snow-covered land and the ice-free sea surface. Jet streaks have wind speeds as high as 217 miles per hour or 350 kilometers per hour. So here in this figure we map the view of a jet streak with the associated region of horizontal divergence and convergence aloft. The contour lines shown are ice attacks. They're lines of equal wind speed, and these are shown in kilometers per hour. So in a straight jet streak, the strongest horizontal divergence is in the left front quadrant, supplying upper air support for an extratropical cyclone development. These jet streams undergo seasonal shifts, so they strengthen in the winter and weaken in the summer. And we also see that in the summer, the jet stream is north, and in the winter, the jet stream is south. When the polar front jet stream is south of your location, the weather's going to be cold. When it's north of your location, the weather's going to be warmer. We also have a subtropical jet stream. This is found on the poleward side of the Hadley cells, and it's near the break in the tropopause between the tropical and middle latitudes. It's strongest in the winter, and it's less variable with latitude than the polar jet stream. Other jet streams include the tropical easterly jet. This is a feature of summer circulation at about 15 degrees north over North Africa and south of India and the Southeast Asia. We also have low-level jet stream, several meters above the Earth's surface, and it surges up the Mississippi River Valley, and it contributes to the development of nocturnal thunderstorms. Now we want to talk about El Nino, La Nina, and the Southern Oscillation. So in El Nino, the trade winds weaken, and the sea surface temperatures rise well above the long-term averages over the central and eastern tropical Pacific. These are areas of heavy rainfall that shift from the western into the central tropical Pacific. La Nina is a period of exceptionally strong trade winds and across the tropical Pacific with the lower than usual sea surface temperatures in the central and eastern Pacific. El Nino is the warm phase of La Nina, is the cold phase of the tropical atmosphere-ocean interaction. El Nino and La Nina influence the prevailing circulation of the atmosphere in the middle latitudes, especially in winter. So this brings weather extremes that may accompany the El Nino are opposites those associated with La Nina. So on the historical perspective, originally this was a name given by fishermen to the seasonal occurrence of unusually warm southward flowing ocean current and poor fishing off the coast of Peru and Ecuador during the Christmas season. So the warm weather episodes are relatively brief, 1 to 2 months, and the sea surface temperature in the fisheries return to normal levels. We now reserve this term, El Nino, for long-lasting atmospheric ocean anomalies. So they occur every 3 to 7 years, and they persist for 12 to 18 months or longer. They're accompanied by significant Pacific sea surface temperature changes and major changes in the atmosphere and ocean circulation patterns, and the collapse of important South American fisheries. An important step in understanding El Nino was the discovery of the Southern Oscillation in 1924 by Sir Gilbert Walker, and what he saw was a seesaw variation in air pressure across the tropical Indian and Pacific Oceans. And these influences monsoon rains in India. In 1966, it was demonstrated that a relationship between El Nino and the Southern Oscillation, ENSO, and an El Nino episode begins when the air pressure gradient across the tropical Pacific begins to weaken, heralding the slacking of trade winds. So an intense El Nino of 1982 to 83 brought attention to weather impacts worldwide. So today the Southern Oscillation Index is computed by subtracting the Darwin pressure from the Tahiti pressure divided by the standard deviation of that quality. So strong positive values, shown in blue, indicate La Nina, and strong negative values indicate El Nino conditions. If the Earth did not rotate, frictional coupling between the wind and the ocean surface would push a thin layer of water in the same direction as the wind, and the surface layer would drag the layer beneath it. But because the Earth rotates, the shallow water of the surface water is set in motion by the wind, is deflected to the right of the wind direction in the northern hemisphere and to the left of the wind direction in the southern hemisphere. This happens except at the equator. Each of the layers of water is put into motion by the layer above, and it shifts direction because of the Coriolis effect. The model to plot the direction and speed of water layers is known as the Ekman spiral. And what we have is a net water movement of 90 degrees to the wind direction due to the coupling between the wind and the surface water is known as an Ekman transport. So what we see is the wind is blowing, and although that it's trying to pull the water surface with it, what we see is that we actually get a spiraling of the wind direction as we go deeper into the water. So in the northern hemisphere, the surface layer of the water moves at about a 45-degree angle to the right of the wind direction. So the net transport of water through the wind-driven column is 90 degrees to the right of the wind. So typically, southerly or southwesterly winds blowing along the west coast of South America drive the warm water to the west, to the left, westward via the Ekman transport and away from the coast. In a process known as upwelling, cold, nutrient-rich water moves upward from a depth of 200 to 1,000 meters. The abundance of nutrients brought to the sunlight surface spur an explosion of the growth of photoplankton, which support a highly productive fishery. Here shows the average rainfall per day across the tropical Pacific from 1998 to 2007. So we see the dark green is about 10 millimeters per day, and the white is 0. So not surprisingly, we see a lot of rainfall near the intertropical convergence zone near the equator. The Walker circulation, or the large convective type circulation, we have high sea surface temperatures in the western tropical Pacific lowers the surface air pressure, and low surface sea temperatures in the eastern tropical Pacific raises the air pressure. So during neutral conditions, the east-west sea surface temperature gradient reinforces the trade winds by strengthening the east-west pressure gradient. The trade winds become warmer and more humid as they flow over the ocean surface. In the western tropical Pacific, warm humid air rises, expands, and cools, leading to thunderstorm formation. Aloft, the air flows eastward and sinks over the cooler water of the eastern tropical Pacific. So what we get is a picture that looks like this. We get a convective cell because at the equator, what we're going to see is that we'll end up with warm, moist air rising up through the atmosphere and producing these violent thunderstorms. There'll be subsiding air that will come across and fill in where these warm, moist air has risen through the atmosphere. During the warm phase, El Niño, air pressure falls over the western tropical Pacific and rises over the western Pacific. This pressure gradient weakens the winds, and winds slacken and may even reverse direction west of 180 degrees longitude. A thick layer of warm surface water drifts slowly eastward over the tropical Pacific. In the western tropical Pacific, sea surface temperature drops, sea levels fall, and a thermocline rises. And in the eastern Pacific, sea surface temperature rises, sea level rises, and the thermocline deepens. Upwelling is blocked, fish harvests plummet, and coral bleaching occurs. El Niño has a ripple effect on the weather and climate throughout the world. A linkage between the atmospheric circulation changes in widely separated regions of the globe is known as a teleconnection. In 1997-98, the El Niño rivaled its 1982-83 predecessor as the most intense in the 20th century. So here we see the opposite happening. So if you look at the cold phase of La Nina, here there's a period of unusually strong trade winds and exceptionally vigorous upwelling in the eastern tropical Pacific. The sea surface temperature anomalies opposite those of El Niño. And although the magnitude of the anomalies are not as great, typically 2 to 3 Celsius degrees below the long-term average. This brings about the opposite temperature weather extremes than El Nino. And these are shown here. If we look at the frequency of El Nino and La Nina, the NOAA Climate Prediction Center launched its new ENSO alert system in February of 2009. El Nino or La Nina watch issues when conditions in the equatorial Pacific are favorable for the development of El Nino or La Nina, and they're issued when the conditions within the next 3 months. An El Nino or La Nina advisory is issued when El Nino or La Nina conditions have developed or expected to continue. Here we see a table of El Nino and La Nina events since 1950. Note that they're not periodic and they have various lengths. So in 1982 and 83, the weather seemed to go wild in many parts of the world as a result of a newly discovered phenomenon, El Nino. This spurred further research on the atmosphere-ocean circulation changes. In 1997 and 98, El Nino rivaled the 1982-83 El Nino as the most intense of the 20th century. Here we can see the evolution of the 1997-98 El Nino. So these are sea level relative to the average in centimeters, and lower, cooler water, higher, warmer water. So, a word on prediction and monitoring. Some empirical and dynamical numerical models have been developed, and their overall results have been mixed. The dynamical models performed well in detecting the onset of the 1997-98 El Nino due to an increasing amount of ocean atmospheric observations data from the tropical Pacific. The ENSO observing system, which consists of an array of moored and drifting buoys, island and coastal tide gauges, and ship-based measurements and satellites. One component is an array consisting of 70 deep-sea moorings. We also have the TOPEC and Poseidon and TRMM satellites, also essential to monitoring the conditions. So here shows the ENSO observing system. The red dots are moored buoys. The yellow dots are tide gauge stations. We also have the satellite data relay and the drifting buoys and volunteer observing ships. So we see the sea level record at a location along the equator in the eastern tropical Pacific derived its measurements made by Topek and Poseidon satellites. And we also see a picture of one of the buoys that were used. Okay, that ends today's lecture, and thank you for your time.